Given 2 points in space, we would like to describe the vector that passes through them and then reorient it at the origin. The way we do that is we create the vector PQ, and it's the vector of differences in coordinates. We're not subtracting points, we're taking a vector of the difference here. This vector here would be oriented at the origin and would be parallel to the original line passing through these 2 points. If I want to do the same process in 2 dimensions, I'd create RS. And again, this vector here would be oriented at the origin. We're going to use this process to describe lines in 2 and 3 dimensions now. Now consider a line passing through the point x0, y0 with slope m. We know from the point slope formula that the equation would just be y minus y coordinate equals slope times x minus x coordinate. But we would like to do the same thing we did with vectors a moment ago and create a vector. If I take any other point on the line, just call it x comma y, there are infinitely many, then the vector I've created would be the vector x minus x0 comma y minus y0. If I then said let's move that down to here, now since there are infinitely many choices, there would be infinitely many lengths of this vector. So what we'd want to do is have a scalar multiple of this. So the easiest way to do that would be this vector right here has to have slope m. So if we use the vector 1 comma m, it's easy to see that the slope would be m over 1. And therefore, if I took every scalar multiple of this, I would get the following equation. Now, if I equate the pieces, I will see that x minus x0 equals t, y minus y0 equals mt. Now, it's an odd way to talk about a line, but if I continue, then I can say the parameterized form of this line would be the following. For every value of t, we would get a point on the line. Now, to make sure that this is actually correct, if I replace t with x minus x0 in this statement, notice we get the original equation, so we know that this is valid. Now, as impractical as this may be in 2 dimensions, this is exactly how we're going to do it in 3. Now let's consider we have a line in 3 dimensions that is passing through the point x0, y0, z0 in the direction of the vector ABC. Now what we'd like to do is parameterize this the same way we did it in 2 dimensions. And what we will do is we will say, if I take a second point on the line, x, y, z, then the vector passing through these 2, x minus x0, y minus y0, z minus z0, must be a scalar multiple of this vector. Because remember, there's infinitely many x, y, z's I can choose, so there'd be infinitely many lengths of this vector. Now when I equate the positions like I did before, I would get x minus x0 equals at, y minus y0 equals bt, z minus z0 equals ct, or more specifically, x equals x0 plus at, y equals y0 plus bt, z equals z0 plus ct, and this is the parameterized version of the line in space. Q, 2, 1, 2, R, 4, 3, 1. Negative 1, 2, 4, 2, 1, 2, 4, 3, 1. We would like to find an equation of the plane passing through these 3 points right here. In order to do that, we need to create two vectors and then eventually take their cross product. It doesn't matter which point we choose as the vertex, but we need to pick one of them. So let's say we pick P. That means I need to find PQ and I need to find PR. So like before, I take the difference in the coordinates, so 2 minus negative 1, 1 minus 2, 2 minus 4, and then PR, 4 minus negative 1, 3 minus 2, 1 minus 4. Now between these two vectors here, I'm going to take the cross product to get the normal to the plane. Now the simplest way to do cross product, despite what you may have seen before, is to simply stack your vectors and then use the equation, which is this minus this. So 3 minus negative 2, negative 10 minus negative 9, and 3 minus negative 5. Now, I'm pretty sure I did this correctly. The simplest check of all is to now do a dot product with either of these. So if I do the dot product here, I have 15 plus 1 minus 16, that's 0. 25 minus 1 minus 24, that's 0. I now have absolute certainty that I have the correct normal vector. Now to find the equation of the plane, I need to use one of these 3 points. It doesn't matter since all 3 are on the plane, so let's use the first one. And now I'll find the equation of the plane is simply 5 times x minus the x coordinate, negative 1 times y minus the y coordinate, plus 8 times z minus the z coordinate, and that must all be 0. So 5x plus 5 minus y plus 2 plus 8z minus 32 is 0. Or finally, 5x minus y plus 8z minus 25 equals 0. I can have certainty by taking any of the 3 points and checking to see that they satisfy this. But this is how we find the equation of a plane in 3 dimensions.